So now we define the determinant of a matrix. So the determinant of an n by n matrix, right? Determinant is only ever defined for square matrices. So it's denoted det A, sometimes with the flat bars A, so it looks like an absolute value, which is misleading because determinants can definitely be negative, but whatever. So the official definition is, it is going to be a sum over the set of permutations of length n, and for each term we have the sign of the permutation, and then we multiply it against the entries a sub 1 sigma 1 times a sub 2 sigma 2 times and so forth out to the n. Now notice that this is a sum over all permutations, so there are going to be n factorial terms in this sum because there are n factorial permutations of length n. So computationally it quickly becomes unwieldy, but theoretically it has some interesting properties. Let's look at an example to see what this grotesque formula actually means. So if we go back to our example of the permutation 3, 1, 2, it's sort of a friendly way to think of it as looking at the corresponding permutation matrix. So here we have there was a 1, and so 3, 1, 2 means there's a 1 in the third, first, and then second entry, right? And so you should think of this as selecting these entries from A. So in other words, if we look at A here, then what we're doing is we're picking up the A13 entry and the A21 entry and the A32 entry, and that'll be what goes into our summation for that particular choice of sigma. It'll be the product of those three. Okay, and so we saw that this was a positive permutation, so it's going to be a +1 times A13 A21 A32. And we can also think of this term and so now I'm just going to explain a little bit about how my definition is slightly different from the book's, but only superficially, and if you look at it closely you'll see it's actually a different way of writing exactly the same thing, and that's because the way that I wrote it here, I have the sigmas appearing as the second index. The book has it appearing as the first index. This makes it slightly more natural to explain something that I want to show, but since it's being summed over all permutations, it actually doesn't make a difference. They're equivalent, and that's what I want to explain right now, how it doesn't matter if the sigma appears in the first or second index. So notice that this term right here can be rewritten as +1, and now so the way that I have it written here, it's ordered by I have it increasing in terms of the first index, but I could rewrite exactly those same terms in terms of the second index. So here's where the 1 appears. So I would have A21, And then, so that's my 1, and then my 2 is the second one in this one. So I'd have A3, 2, and then my last one, A1, 3, right? And so this now looks like +1, and then I've got a tau 1, 1, a tau 2, 2, and a tau 3, 3. So they're written the same way that the book writes it there, yeah? And if you want to know what that tau is, it's just the inverse of sigma, which is, so because what did we find? We've in the rewritten version, we had 2, 3, 1 as our indices right there, right? 2, 3, 1. And if you want to check that that's the inverse of the given sigma that we started with, you can either work it out by transpositions, or you can look at the corresponding permutation matrix. So this is 2, 3, 1. And that one's maybe easier to check because the multiplication right there says, oh, well, we look at, so here's our tau. And then what was our sigma? It was 1, 1, 1. And when you do the product, you find things like, let's see, so first row, first column, oh, look at that. It hits up, picks the 1. We get the 1. And then for each of the other two, we're going to get 0. And continuing in this way, you see that we get the identity. And this can also be done if you interchange the roles of these. So the sigma matrix times the tau matrix. So either order you put it in, you'll get the identity. So it must be the inverse. Okay. So from this we can make observations. So for example, the determinant of A is the sum over all sigmas in perm n sine sigma, and then we've got A1 sigma 1, AN sigma n, and then we can rearrange. So the second index is increasing. That's what I did just above. And then this gives you the sum over taus in perm n. Actually, we just saw that that if you rearrange it so the second index increases, that actually gives you sigma inverse. And this is, well, here, I'll do it in 2 steps. So we do tau, sine tau, and then this is A tau 1, 1, A tau n, n. And then we use the observation that tau is equal to sigma inverse. And then that lets us know that a couple things. So for one, the sign of sigma inverse is the same as the sign of sigma, because if it takes 3 transpositions to get you there going one direction, it'll take you 3 transpositions to get you back going the opposite direction. And so this is going to be the sum over all sigma inverses in perm n of sine sigma inverse and So with this observation about the sign, that becomes sine of, well, actually, I don't even need to do that. I can just say at this point that here we've got we're summing over a dummy variable, and it doesn't matter what we call as the dummy variable of summation. We just need something that runs over all permutations, and so now I can I can call that sigma by doing basically like a u substitution, but for a sum. And so then that allows me to write it the same way that the book does. Whoops. Which is in terms of just sigmas like that. Okay, so long story short, it doesn't matter if you have the subscripts written with the permutation on the first or the second. Either way will work. I like doing it this way for something that will come up in just a moment. So one example with this then is that's important. I would actually have called this like a lemma or something, but it's worked out as an example in the book, so I'll stick with that. So suppose we look at the case when we have a matrix which is upper triangular. Okay. Then the determinant of A is going to be the product of diagonal entries. So you just multiply together the things on the diagonal. And this is familiar to you from your previous course in linear algebra. So the product of diagonal entries is the product of the entries whose indices are equal. And so the proof for this, such as it is that if we look at any permutation other than the identity, then you'll see a row swap. Oops. Puts a 1 below the diagonal. And so here I'm thinking about a permutation matrix. So that means that, in other words, you're going to be selecting an AJK with J greater than K. So in other words, something from underneath the diagonal to be in your sum. But then this is 0 down in this region because we've got an upper triangular matrix. So then that means that that term vanishes from the sum. So then that means that only the term for the identity permutation survives. And that one gives you exactly the product of the terms on the diagonal. So that's it.